Okay, well, we're going to go ahead and do 2.3 postulates and diagrams. First thing we want to do is review a bunch of postulates here, things that we've talked about a lot this year. So the first one, through any 2 points, there exists exactly one line. All right, and that is, that is called the 2-point postulate. And let me give an example of that. So through any 2 points, so let's say I have point A and point B, you can make only one line through those 2 points, one distinct line. All right, and we'll call that line L, or you could call it line AB. All right. Another one that kind of goes with that is called the line point postulate. All right, and the line point postulate says a line contains at least 2 points. So line L contains points A and B. All right. Now it could have more points, however, it contains at least 2 points. All right. So things that we've talked about. Another one, if 2 lines intersect, then their intersection is exactly 1 point. That is called the line intersection postulate. They get really creative with the names here, you know. 2 lines intersect and their exact intersection is exactly 1 point. So for instance, if I had, say, line L and line M, they would intersect at point, we'll call that point P. Okay? Through 2 lines intersects exactly, or 2 lines intersect at exactly 1 point. Whoops. All right. I should actually make that L look more like an L. Otherwise, that type A in me is going to be bothered. Won't be able to sleep tonight. Okay, there we go. All right, the next one. Through any 3 non-collinear points, there exists exactly 1 plane. That is called the 3-point postulate. And really, that's taking a plane. So let's just make a plane there. We'll call it, say, like plane P. Okay, and plane P through any 3 non-collinear points, maybe like A, B, and C. Okay, there exists exactly 1 plane. Now that's non-collinear. Remember, if they're in a straight line, think of like a book's binding, you could have an infinite number of planes. But if it's non-collinear, it kind of forms that triangular shape, then there only exists 1 plane through those 3 points. If you kind of think of like a stool with 3 legs on it, you could only put one top on that stool. Okay, that top would be the plane. Another one that goes with that, a plane contains at least 3 non-collinear points. Okay, so if you have a plane, for instance, plane P, okay, if you have a plane for like plane P, it has to have at least 3 non-collinear points. Otherwise, you can't have a plane. So these 2 postulates go hand in hand. This one is called the plane. Oops, not plane. Plane point postulate. Okay, the plane point postulate. A plane contains at least 3 non-collinear points. Okay, the next one. If 2 points lie in a plane, then the line containing them lies in the plane. So, once again, we have a plane. Okay, we'll call plane R this time. In plane R, if 2 points lie in that plane, so for instance, let's just go with A and B again, then the line that would go through those 2 points also has to be on that plane. That's what that's saying. Okay, and then I think I've got one more on here. Yeah. Oh, by the way, this is called the plane line postulate. can almost like guess these names, but you know, there we go. It gets kind of wordy once you have them all in your head. Then you kind of might mix them up. If the last one, if two planes intersect, then their intersection is a line. This is called the plane intersection postulate. Okay, and so really, if you think like the corner of a room, wherever you're sitting, if you look where the two walls come together, that's really what we're talking about here. So if, for instance, if you have a plane running, I don't know, let's just have it go like that. And then we have another plane coming down through that. You know what? It's going to be here. I didn't give myself enough room, so let's actually fix that before it becomes a big issue. All right. So why don't I start with the vertical plane? I have a plane running vertically like so. Okay. And then I have another plane that's going to go through and hit that plane in two spots. Okay, in the front and the back. It's going to poke out this way like a big three-dimensional plus sign if you think of it like that. Okay. And unfortunately, I didn't put some dashed lines in there. Do that. Okay, this line will be solid. This line will be solid. However, this line that's back there and hidden is dashed until it gets through there, which is solid. And I actually have one other dashed line. And I'm getting real picky on this, but I would expect it in my class. So there we go. All right. So you have two planes. We'll call it plane S and plane T. Okay, and those two planes intersect at this line right here. All right, and maybe we call that line L. All right, two planes intersect, then their intersection is a line. There, we've got it. All right, so we have these different postulates. Now we can actually talk about what that looks like. So if we're sketching some diagrams, let's sketch a diagram. AB, this line means, or this symbol means perpendicular, is perpendicular to line BC. Let's say I have line AB. Define that by putting an A. And we have line BC. Now, notice what I did here. You're not drawing along because what I've done is I've actually started drawing another line, and this is what I see a mistake with. Oops, that looks like an E right there. I see a mistake a lot of times like this in my class. Where we may have AB and then BC, but notice I can't have the same point appear twice, or a point with the same twice in the same diagram. What I need to do is, if B on there already, then I need to make sure that my line is coming down through that point. Okay, so this would be B and C. So notice I've used B that appears in both twice. Or excuse me, only once in my picture, but I've used it in both of those lines. And to show that they're perpendicular, I put my right angle. That's one way to draw it there. AB is perpendicular to BC. All right, let's use another color for the next one. We'll go line M bisects SR. We'll segment SR first. Make it's an S, not a 5. And I have line M, and it's going to bisect. Okay. Now, that's not the best looking bisector, so I know that we go by markings and not necessarily looks, but I'm going to try to make it look a little better. Okay. So I have line M, and it bisects SR, and the way we're going to show that is just by putting little marks here. That little tick mark and that little tick mark. And let's go ahead and label this. Since they didn't tell us what to label, we'll label it P. SP is congruent to RP because these markings show that. Okay. So we want to have our congruent markings there. So if I have one mark on that side, I have to have one mark on that side. If I had two marks over here, I then have to have two marks over here. Okay. All right, segment MN is perpendicular to plane C, and plane C bisects MN. Holy moly. All right, so first thing, go ahead and draw plane C. There's plane C. And MN is perpendicular to plane C. So that means I have a line that starts up here, goes, hits plane C, and punches through, and then comes out the other side of plane C. Okay, this would be maybe M, that would be N. Okay, so we have M, and you know what? Let's use our capital letters. Whoops. Let's go ahead and, since we used caps there. All right, and we're going to show that they're perpendicular by putting a right angle marking there. In fact, I'm going to label that point P, okay, where it goes through the plane. So think of it like a piece of paper, which is plane C, and the pencil poking through plane C, okay, and that would be segment MN. Okay, going through it right, and the plane has to bisect it, meaning, let's go ahead and switch up colors here, meaning segment MP is going to be congruent. So MP is congruent to NP. All right. And the next one, plane G intersects plane H in EF, and point D lies in plane G, and then DE is perpendicular to plane H. Wow, that's a lot of stuff there. So let's start with that. Plane G intersects plane H at EF. So let's think back to what we've done before. Two planes intersecting, like S and T here. Okay, that's the first thing I'm going to do. I'm going to go ahead and draw one plane. Plane G, and I'm going to have it intersecting. Oops, let's try to. Okay, we're going to have it intersect plane G at this line. Which we are calling EF. Okay. And, oops, let's go ahead and finish that plane. That's plane H. All right. And then point D lies in plane G, and DE is perpendicular to H. So point D has to lie in plane G in a way that the line that goes through D and punches through E, like so, is perpendicular to plane H. All right, so it might help. Let's do this. It may help just a little to use a different color. And that could help you as well if you were doing these. Okay, so I have this as point D, and I'm going to highlight point E here. All right, and that is perpendicular to plane H. Now remember, this one's plane H, so that means I would have to have a right angle marking going like so to plane H. Wow, that is quite the picture there. All right. Good to double check your work there. So point G, or plane G, intersects plane H at EF, line EF. Point D lies in plane G, okay, and DE is perpendicular to H. Okay. Well, let's go on. Can the statement be assumed to be true? Okay, well, let's see. AB, so ray AB and ray AD are opposite rays. So really what we're doing in this last section here and our new section, really was using our postulates that we looked at the very beginning. Oops, I'm trying to go back through them. These postulates and diagrams, hope you have them in your notes. We're looking at those, and we're seeing if they can be applied to these, and if they help us to make these true. And our markings, looking at our markings. So ray AB and AD are opposite rays. So I have ray AB, so starting here at A, extending that way, and ray AD, starting here at A and extending that way. They are opposite rays. Well, yeah, they both start at A and they extend in opposite ways, making a straight line. So yes, AB and ray AD start at the same point and extend in opposite directions, is one way to describe it. All right, now I'm going to switch colors so we can do the next one. Angle BAC, so we now have B to A to C, and CAD, C to A to D, so this angle and this angle. Okay, those two angles, if I were to trace them, are supplementary. Yeah, they make a straight line. They add up to 180, so that is true. Angle BAC and angle CAD form a straight angle. All right, and straight angles are 180 degrees. How about BAC? You know what, let's switch colors while we're thinking about it here. BAC is congruent to BAE. So we now have BAC, so this angle right here, and BAE, this angle right down here. What we want to know is if those two angles are congruent. Well, we know that they make a linear pair because they form a straight line. And we know that BAC is 90 degrees. And if they make a linear pair, and one angle is 90 degrees, the other, BAE, has to be 90 degrees because a linear pair is 180 degrees. So, yes, angle BAC, the measure of angle BAC, is 90 degrees, and angle BAC and angle BAE form a linear pair. So, angle, the measure of angle BAE must also be 90 degrees. All right, there we got that. So, we're kind of working our way towards proofs, which is really what we were trying to do these last few lessons. Last one, CE is perpendicular to plane S. So let's see if I have any other colors that I can still see available. We'll try orange. Line CE, so this one right here, ooh, that one's a really tough color, okay, is perpendicular to plane S. Plane S is the plane running. Let's highlight that one. So, oops, not erase, but highlight. So we're looking at this plane right here. All right. Well, we can see right in here that there is a right angle marking. That right angle marking shows that this line, CE, is perpendicular to plane S. So yes, the right angle marking shows line CE perpendicular to plane S. All right. Very cool. Well, we have a couple more, and just so you know, we're done after that. So I know this is a bit longer video, but trying to go through all these to get us ready for proofs. BD lies in plane S and in plane T. So let's see. BD, this line right here, lies in both plane S and plane T. So you'll notice that is the intersection of the two planes. So yes, BD is the intersection of plane S and T. I guess it's planes S and T. All right, and we'll go ahead and try the next one. If G is a point in plane S, then CG lies in S. So let's go ahead and just make G a point. There we go. Then CG, that would be this line right here. It would extend from G all the way up through C. Okay, and it would punch through plane T at that point. So really, I should, if I'm going to do this accurately, I should actually have it start here at G, go up to C, and then I should see a dashed line as it punches through. Okay, so it comes out the back there. And so the answer is no. It's actually starting on plane S, and we'd actually see a dashed line back here as well. Okay, it would punch through, whoops. It would punch through S, and then it would punch through plane T. So no, that's not the case. Okay, CG does not necessarily have to run or go through, lie on plane S. It could intersect plane S at point G. It could, I guess we should put the word only. It could only intersect plane S at point G. Okay. All right. How about CE bisects BD? Well, let's try that one here. So CE bisects plane or segment BD. Well, you'll notice that we have markings right here, this marking and this marking. And the points that those two markings are between are C and A and B and A. So if we think about that, that means BA is congruent to DA. Did I say CA? I meant DA. Okay, oops, not DC. My goodness, I'm thinking too much of my comics. All right. DA, duh. All right. BA is congruent to DA, and therefore, since that's the case, CE is bisecting those because of our markings there. It's bisecting BD because of the markings. So that is yes. And you can use this as your reason. Okay. And then plane T bisects BD. So we got plane T, and it bisects BD. Now, a plane can't, in this case, it's not going to bisect BD. Okay, it goes through BD, but it doesn't necessarily bisect it. So no, that is not the case there. In fact, BD lies on plane T, and since it's lying on plane T, the whole line lies on it. It cannot bisect it in that case. So no, plane T contains line. Well, you know what? I was going to say line segment, but let's just actually use the symbol segment BD. So it's not going to bisect it. All right. Well, good luck on your work there. Woohoo!